Assalamu alaikum and good day to all. For this week class is about material properties chart. This chart is available in the CES Pack software in the materials selection laboratory. Also, you can find it the Ashby book. In this lecture you will learn the type of the charts, how to use it, and what materials can be choose based on the material's various properties. By the way, this lecture is spoken using Balaboka software, so it will be like England's English voice. Here is the outline of this lecture. First, is the introduction and synopsis. Second, is exploring material properties. Third is the material property charts, which is the Modulus density chart, the strength density chart and the Modulus strength chart. Also, there will be the cost bar charts and the Modulus relative cost chart. Fourth is how to utilize SYNOPSIS software for material selection process. Finally, is the summary and conclusions. Introduction and synopsis. Based on design requirement, you will have range of material properties, for example, the operating temperature between room temperature and 250 degrees Celsius. Modulus of elasticity no less than 120 GPa, and many more. Hence, you need to determine the material properties limit performance. Basically, one property can be displayed as a ranked list or bar chart. You will have to rank several type of material properties. Seldom the performance of a component depends on just one property. More often it is a combination of properties, for example, the need for stiffness at low weight, thermal conduction coupled with corrosion resistance which is related to oxidation resistance, and the strength combined with the toughness such as use for building materials. Once you have decided the limit of the material properties, you can plot one property against another, mapping out the fields in property space occupied by each material class and the subfields occupied by individual materials. Hence, you will get the materials properties chart. They condense a large body of information into a compact but accessible form. There are two type charts. The first one is a bar chart, which is a single property of material plot against all material in their own respective family of materials. The second chart is a bubble chart, which is the plot of two different properties such as Young's modulus and density against all materials available in the database. Here, you can see some materials from different family of materials are overlapping, such as shown in the bubble chart. Selection charts are really useful as in showing the trade-off between two properties, because the charts plot combinations of properties. Example, if we want a light and stiff material, we need to choose materials near the top left corner of the chart, so composites look good. Materials of each class, example metals, polymers, form clusters or bubbles that are marked by the shaded regions. We can see immediately that metals are the heaviest materials, foams are the lightest materials, ceramics are the stiffest materials. Here is the strength density chart. Strength in this case is fracture strength sigma F. As per previous class about the mechanical properties of materials, the strength for metals and polymers are referring to the yield strength. For brittle ceramics, it is referring to the modulus of rupture. For elastomer, it refers to the tensile tear strength. And for composites, the strength means the tensile failure strength. From the chart we can immediately see strength is correlated to density, so that most materials lie on the bottom, left to top right diagonal. High strength at low weight is so often important that a property called specific strength is defined as strength/density. The bubbles are elongated along the strength axis, but not density. This is because alloying and heat treatments have a strong effect on strength but little on density. The yield strength and tension for all materials, except for ceramics for which compressive strength is shown, their tensile strength being much lower. Composites provide a means of achieving high strength at low weight, because they exploit very strong fibers in light matrices. This chart is useful for identifying materials for components which require high strength combined with low weight. Top left on the chart. Woods are somewhat like polymer foams, having pores full of air, and so float in water, but achieves high strength at low density by its efficient cellular microstructure. Quite easy. Hang on a tick. What are those dotted line on the chart surface? You will now learn to read and use contour lines, selection lines, meaning of y-intercept, materials index. Here is the lines that you need to know and how to use it. Contour lines, selection lines, slope of selection lines, meaning of y-intercept, materials index. This is the Young's modulus vs density chart for deflection limited design, and when weight is also important, such as in transportation. To the upper left is the light and stiff region. Lower left is the light and soft region. Lower right is the heavy and soft region, and lastly, the upper right is the heavy and stiff region. Hence, we would know the rank of materials family in term of lightweight will be foams, followed by composites, then ceramics, polymers, and lastly metals. Also, the Young's modulus is related to the atomic bond, S note and R note, which is the atomic spacing. If the atomic bond is strong, it will contribute to stiffness. The atomic spacing contribute to the density. The true meaning of selection lines and contour lines in bubble charts. Selection or contour lines of slope 1. Meaning of y-intercept. Selection or contour lines of any gradient which is equivalent to 1, bigger than 1 and lower than 1. Ashby charts are plots between material properties on a log-log scale, so that a family of parallel contour lines with a particular slope in the chart gives us a guideline to optimize a particular merit index M. A particular line with some slope links materials with equal performance. In this case, the line shows the performance of the materials in term of stiffness and lightweight, represented by material performance index M, which is equivalent to Young modulus E in gigapascal divided by density rho, where the actual meaning is index M is proportional to E and is proportional to its density rho. Y-intercept is log M, which is intercepted y-axis. Similar as the function y equals mx plus h, where h is the intercepting value at y-axis. The contour lines of slope 1 means m equals e power of 1 divided by density. Slope 2 means m equals e power of 1 per 2 divided by density, and so on. Contour or selection lines. The maths for the case of linear relationship. Index m equals e divided by rho. M equals depends on the imposed functional relationship between the e and rho. Linear in this case. Solve index equation for e equals m rho, which is similar for like equation. Y equals x function. Equation of a straight line. Slope m. Through origin. Taking logs of this equation, you get log e equals log rho plus log m, where log m is the y-intercept. For example, all parallel lines with a slope 3 show different values of the merit index m equals e power of 1 per 3 divided by rho. A guideline of slope 3 is shown in the chart, and is displaced upwards, retaining the slope, to maximize the merit index m equals e power of 1 per 3 divided by rho until a reasonably small subsets of materials are isolated above it. Glass lies on the line m equals 2, GPa, 1/3m3 milligrams. Materials which lie above this guideline are better, those far below are not so good. The contour lines and its linear relationship are actually depending on the log scale of the Young's modulus. Originally the performance index, m, is equivalent to Young modulus, e, divided by density, rho. Then you can see the linear graph on the left. At the left linear scale graph, as you increase the m value from 1 to 10, and to 100, you can see the increase of other linear lines to a steeper slope. This means with the increase of index m, the young modulus increase more per kilogram. Rearrange the equation, you can get young modulus, E equals m times rho. Now, change the equation in the form of log equation, you will get log E equals log rho plus log m, as you already know, that the y-axis intercept is actually the log m. Using the log form of the equation, you can get the graph on the right. Compared to the left linear scale graph, the log graph can show you the intercepting value more clearly. Here you will understand that the use of y-axis intercept is to move the slope upwards as a guide to choose materials that have similar performance. This is the screenshot of the interface in the CES software. On the selection data, you can selection material universe EDU level 2. EDU level 1 is the introductory level of materials, where you have a limited data with less than 70 materials and less than 80 processes. In EDU level 2, you have less than 100 materials and less than 110 processes. In the selection stage, you choose density and young modulus. Then, you will get the density versus young modulus bubble chart. At the chart, the slope chosen will be 1 and m equals 10. Then you can observe the intersecting slope with y-axis will be at 1.
Next, is when the contour line is the nonlinear such as exponential graph. When you change it into logarithmic graph you can get a straight slope. For example, as per equation m equals square root e divided by rho. When you rearrange the equation and then change into the logarithmic form you will get the slope equivalent to 2. By the way, why in the world that e need to be square rooted? The reason of why the difference of the indices is based on the shape of the object itself. If the objective is to minimize mass, the smaller the cross-section of the material, the smaller the force required to deform them. Hence, the minimum requirement need to be increased significantly. In the bubble graph, the contour line of slope 2 becomes steep and the selectable materials above the contour line become lesser than that of the slope 1 contour line. Here is the difference between the linear graph in the left and the logarithmic graph in the right when the slope is equivalent to 2. Next, the screenshot of the software when the slope is 2. Here, when you try to calculate index m, the value will be 3.16. Now, you can see the differences when you change the slope. Note that the materials lower than the contour line, the one colored gray, are the non-fit to be the candidate materials. This is the strength sigma F versus density bubble graph. Similar as the Young modulus versus density, you can also derive the index m at various slope. The difference is the equation for m, where m is equivalent to strength, divided by density. Then, from this equation you can rearrange and change it into logarithmic form equation to get the contour lines. Here the slopes can also be 1 or 1.5 and 2. But the in the equation m will be equivalent to square root 2/3 of strength divided by density for slope 1.5 and square root of strength divided by density for slope 2. Continues from the previous slide. Here you can see the bubbles of several material families is narrow towards the density direction because the density is almost the same with different strength. For example, their red bubble is the aluminum alloys bubble. As you know, there are several series of aluminum alloy from 1000 series to 7000 series. Each series have different alloying compound and concentration, to be applied on a specific application such as marine materials, automobile, and so on. Nevertheless, all of the aluminum alloys having almost similar density despite different strength values. You can refer the properties of aluminum alloy in the ASTM Metals Handbook Volume 2B. Elastic strain are related to Hooke's law, where yield strength is equivalent to the modulus of elasticity multiplied by yield strain. Also, using the Hooke's law equation, F equals K times X, the distance change between atom delta R naught can replace X in the equation. The yield strain for metal is smaller than that of ceramics due to its ductility, while for ceramic it has bigger modulus of elasticity where it requires bigger yield strength to be applied. Since the atomic springs can be stretched up to 10%, we can derive the equation into F is equivalent to S naught multiplied by delta R naught. The delta R naught can be changed into R naught divided by 10. Take account that the failure stress is sigma asterisk is equivalent to elastic modulus divided by 10. For polymers this equation is true, but for metals it should be in smaller value due to its metallic bonding. Another useful bubble chart is the Young's modulus versus strength. Here you can see the behavior of materials when force is applied. The lower right of the chart show materials having low Young's modulus, tend to be buckling before yield. The upper right of the chart exhibit materials that is stiff and strong including metal and alloys as well as technical ceramics. As for metal alloys bubbles such as copper alloys, zinc alloys, and steels is stretched towards Young's modulus direction. These metal alloys usually have similar elastic modulus, but with different strength because of the alloying element. Since the alloying element in these alloy are considered very low such carbon inside iron, the Young modulus is near to its parent materials. At upper left of the chart, you will see materials that yield before buckling such as concrete and bricks which in the group of non-technical ceramics. Using this chart, we can also determine its yield strain by dividing the strength with the elastic modulus. The yield strain in this case is the material index that can provide you with contour lines with slope equal to 1, 1.5, and 2. Thus you can choose materials using this contour line at here you want to choose materials with large strain failure or small elastic strain. Another chart that is useful is the fracture toughness versus Young modulus chart. Fracture toughness, K1C, is in unit megapascal meter square root. In the chart, the contour lines you can use is toughness, GC. The toughness GC is equivalent to fracture toughness divided by elastic modulus. The fracture toughness range is large. It varies from less than 0.01 to over 100 megapascal meter square root. At the lower end of this range are brittle materials, which, when loaded, remain elastic until they fracture. For this, linear elastic fracture mechanics works well and the fracture toughness is a well-defined property. At the upper end lie the super-tough materials. All the materials show substantial plasticity before they break. For these materials, the values of K1C are approximate. It is derived from critical J integral, JC, and critical crack opening displacement, sigma C, measurements. The reason metals are dominating engineering materials is that they almost all have minimum values of K1C for conventional design, which is above 20 megapascal meter square root. As a general rule, the fracture toughness of polymers is less than that of ceramics. Yet polymers are widely used in engineering structures. Ceramics, because they are brittle, are treated with much more caution. Next is the specific stiffness versus specific strength. The specific stiffness is actually the Young modulus divided by its density of material. while the specific strength is strength divided by density. Using this chart you can determine which materials are strong, stiff, and lightweight. The contour lines produced by this chart is also similar as elastic modulus versus strength chart, where you will get yield strain. However, the chart shows the bubbles are shifted towards to the left because it is already divided with its respective density. Next is the tutorial part. Remember, you can do it if have access to the software in laboratory. Otherwise, you use it as a reference on how the material selection and chart generation works in CES EduPack software. The engineering properties of materials are usefully displayed as material selection charts. The charts summarize material properties in a compact, easily accessible way, showing the range spanned by each material family and class. By choosing the axes in a sensible way, more information can be displayed. The most striking feature of the charts is the way in which members of a material class cluster together. Despite the wide range of modulus and density of metals, as an example, the clusters occupy a field that is distinct from that of polymers or that of ceramic, or that of composites. The same is true of strength, toughness, thermal conductivity, and the rest. The fields frequently overlap, but they always have a characteristic place within the whole picture. The position of the fields and their relationship can be understood in simple physical terms: bond, packing density, etc.